Thanks, Srikanth and the team for this wonderful stage. Let me introduce myself. I am Guhan, CTO and founder of Aprecomm. So I'd like to start with a small introduction to what we do as Aprecomm. Today, with post this pandemic, the last 2 years, if we see the biggest challenge is to provide reliable connectivity in home, because home has become where post this pandemic, education and work starts from home, right? Happens in the home, and government start spending. They started allocating emergency funds to provide connectivity to rural parts of the country, right? Every government is spending money today to do that, and ISP is also seeing of late a lot of new connection requests. And if you see the small size ISPs which are providing solution for like 100K, 200K homes, are there now targeting to provide solution for 1 million homes, right? So the number of connections which these ISPs are going to serve is increasing day by day. But with this increase in the number of connections, obviously you have a bigger challenge of providing a reliability to each and every service provider, right? So for the service provider, they are very sure at the backhaul they have all the tools to ensure that the backhaul connectivity is good. But when it goes to the last mile connectivity, especially when it goes to the Wi-Fi, they don't have enough visibility. And obviously to provide support to 1 million homes is not an easy job. It has its own cost and it has its own hassles. So they are looking for a solution wherein they can automate this whole support and also have a complete visibility to the Wi-Fi networks. So at Aprecomm, we exactly provide a solution for this problem. So we started around 2016 with a vision to create autonomous networks. So to achieve this autonomous network, we created an AI engine called Evolve. So this AI engine can be deployed in any device in the network, and it can make the device adapt to the needs of the network and auto-configure the device to provide a better performance within the network. So what we did was we took this Evolve engine. So the Evolve engine could be deployed in any device, any network device. It could be a switch, or it could be a Wi-Fi access point, or it could be even a SD-WAN switch in the network. So we being are experts from the Wi-Fi, we have a better Wi-Fi domain knowledge. So we thought of taking this Evolve engine into a Wi-Fi access point. So we created a stack called VWE, a Virtual Wireless Expert, which can actually troubleshoot, and it can also automate the configurations and enhance the experience day by day. So it basically makes the devices to evolve. So we all heard about self-organizing devices, right? So we know the self-organizing devices looks at a certain parameters and tries to organize the device to provide better performance. How about the devices can also organize even before the demand starts? Basically, how about if the device can predict that what is required for you? Let's say in this particular auditorium, it was expected that 60 people are supposed to come and 60 seating arrangements were done. But unexpectedly, 75 people come. Maybe in the first conference, Srikanth realized, okay, maybe whenever I say 60, 75 people are coming, probably the next time I should make sure I arrange 100 chairs for that. That's exactly how the system will learn. So I first predict that this is what is required for me, and I organize the system to provide that kind of configurations. And as I learn over the period of time, day to day, right? So day one, I might have predicted that you might require maybe 100 Mbps of bandwidth, and I see that you are using more than that. And day two, I am started providing you a little better bandwidth. So day to day, the system starts evolving. So the day to day, the self-organizing of the device changes depending on the patterns happening in that environment. So that's exactly what we try to do as part of this Evolve engine. It's not just we want to provide some kind of solution for the problems happening at the moment or problem which has happened little in the past, but we want to provide a solution where the system itself can evolve like how humans are evolving by day. Once the system is deployed in your environment, it starts understanding your demands and then keeps evolving day by day. And so when I say evolve, basically, okay, I'm not able to move to the next slide. Okay. So what I actually mean by evolve is, the first and most important part is I want to continuously monitor the system. I want to understand the various parameters in the system. And then try to understand the changes in the environment, your demand metrics, what type of devices are in that environment. So let's say in a home, typically you might have 7 to 10 devices. And what are the demands of these devices? How are they placed in your home? And what needs to be allocated, or what kind of bandwidth needs to be allocated for this? Then adapt the device, basically change the configuration based on certain level of predictions that I know that today, typically in a week, let's say over the weekdays, you do more of streaming applications, like you work in the, like you do education applications and people work in the office, so they probably use Skype or Zoom. But over the weekends, they start switching, looking at videos, probably Netflix or YouTube. So I can understand the requirements for these two are a little different. In case of Netflix or streaming applications, little latency here and there doesn't matter, because they do have an ability to buffer and then play you the video. But if it comes to interactive application like Zoom or Skype, a small latency in that is felt by the end user. So the dynamics of the whole network has changed here, depending on what the application is being used. So if I know that, if I can learn that very clearly, I can go and change the configuration accordingly. And day to day, I am going to change it. It is not on that day I did something and I left it for it. Every day the system is evolving. So what I need for that, I need a very good feedback system, right? If I don't have a right feedback, so whenever I take a decision, I need to know whether the decision I have taken is right or not. So if I know that my decision today is not really good, I achieved 80% of what I want to achieve, then probably I use that feedback to go improve my system day by day. So the main key here for an evolving system is to detect the problems after you have made the configuration and try to get the feedback post that. So how to achieve this? So this, though it sounds quite interesting, to get this kind of information, you need to do a lot of data mining. You need a lot of data, right? Every small details in the network needs to be digged in. So we need to get that right data. What I mean by right data here, we don't want repeated information. In any network, you see the same kind of things happening again and again. We want to only get the variations which is very critical for us. So every one of you have to be a Rocky boy. You have to dig the right gold, right? Data is gold here. So like how Rocky boy goes and collects every gold in the world, I want to collect every right data in the network to create a system like this. So like in case of gold, how you refine the gold, right? You remove the unnecessary stuff. So we remove the unnecessary repeated information and we look for the right data from the network. The next important thing is every occurrence in the network is required. Like you did a channel change, or your neighbor started coming up with a party and then it is interfering your network. So every occurrence has to be understood. And then comes in the patterns. So what is a pattern? For example, we have very different type of heterogeneous devices in the network. One of the device will have a connection times which is could be within 2 to 3 seconds it might connect. Some device will take a longer time to connect. So we need to understand these patterns and we need to baseline these patterns to understand how better this system can be improved on day to day. And finally, again, the leverage and feedback. So how we take this feedback? So we created an evidential response system. So what is an evidential response system? So whenever I take a decision, let's say I take an example of my system has asserted that the DHCP server in an access point has crashed, right? So for me to assert that DHCP server has crashed, historically if I look at all the devices which are trying to connect to the access point should have not got the DHCP IP. Very simple case, right? Let's say post this assertion is made and a correction is made, the DHCP server has come up. Now I have to see all the devices has to connect. Now I collect these two data, right? I have a DNN model which will try to understand these two metrics. What happened before the problem, what happened after correction. And if these two matches with the decision, that is my evidential feedback system. That system says, okay, you did a good job and it has improved the system by 100%. Your QoE is improved by 80%. So this feedback is again fed back into the system to ensure that it evolves day by day. So what kind of data I have to collect to get into a system like this? So I need every Wi-Fi statistics. I want to understand all the events, the patterns, and obviously I want to correlate the data across various geographies. So whether it is deployed in a specific site, it is deployed across an area, right? ISP wants to know how things are on a specific model, on a specific firmware. So I need to, multi-level learning of data is required. Data is localized to the AP, but I also want to see the data across certain levels or certain boundaries, right? Now to collect that kind of data, what is the size of data we are talking about here, right? I need client movements to be analyzed every second. I want to understand client connection failures, application anomalies, environmental changes. So typically for an AP, we require 34 KB per second. This is okay when it compared to enterprise cases, like where 1000 APs are there. This kind of data doesn't look so big for me. I can still use this data and I can happily deploy my eval engine. But what happened is when we went and tried to deploy this solution across a million homes, the data size is something like 2,700 terabytes of data, right? It is in one day. This is the amount of data we need to process, and it is impossible for us to take all the data to the cloud and do the processing. And that is never going to be a viable solution. So though we have a beautiful AI engine, our next biggest problem came is when we try to deploy this solution, because our solution is not just designed for ISP. It can be deployed in a public Wi-Fi. It can be deployed in enterprise. But when we went to the ISP's market, and if we show this number, none of the ISP is going to work with us, right? Today we have deployed 3 million CPs. With this kind of data, we can never do that. So what we did, okay, so when we spoke to the ISP, right, this is the target they said. Go and reduce your data by 2,500 times. So now, this is a very different challenge. So as engineers, we like to take up these challenges like this, do the impossible, right? I want to still give a self-organizing, evolving system with minimal data. So that is the biggest challenge we took as Aprecomm when we went to the ISPs. So we cannot miss any critical data. We want automation decision should be faster. We should be done scoping. We want to give every issue has to be root cast. We don't want to miss anything out, but still my data has to be smaller. So what can we do? So this is the most interesting challenge we tried to solve. We went back to the drawing board when we pivoted from enterprise to ISP. What to do, how to provide the solution to ISPs. So we applied 3 major principles to do that. So we did decentralize the algorithm. Okay. Whatever the models we created, we thought, let's not keep it in one place. Let's keep it across all the access points. Then we used distributed learning, and then we used distributed analytics. Let me come to one by one here. So what I mean by decentralized algorithm. See, today data is already distributed. No point in collecting the distributed data again and then processing, right? For example, let's say I want to understand when to kick a client to move from 5 GHz band to 2.5. This is a typical band steering algorithm, right? Every client, see, band steering algorithms, the biggest challenge is that you cannot have a fixed threshold. Every client has its own behavior. Some clients will be happy if you go and kick him at minus 45 RSSI also. But some client, if you kick at minus 75 also, he will not connect. Moment a client doesn't connect, you will get a call. My clients are not connecting, I don't know what it is. Right? So every client behavior needs to be understood. Now, if I want to understand every client in a home, there are an average 7 clients. And you think about 1 million houses, like we are talking about 7 million clients data to be sent to the cloud. Right? So this is something not feasible. So it is better to do this correlation within the edge itself. So within the edge, we have an algorithm, we put the model, which can understand each client's behavior. And it will figure out, like for this client at minus 75 RSI, if you go and kick it, that is going to disconnect. It's better not to kick. Let's say that is the decision, or that is the learning, behavior learning I have done. So that learning will happen in the edge. And only the learned data will be sent to the cloud. Instead of sending all the statistics about the client, RSSI, rate and everything, only the required information, dig the right gold, right? Only that is sent to the cloud. Now once that is sent to the cloud, right? Now again, real-time decisions has to be taken. When the client is again connecting to me, I need to make a decision. I don't want that decision to become all through the cloud. So whatever the cloud has learned across the deployments, cloud will push the learning back, distribute the learning, whatever you learned, back to the edge. and leave the edge only to do the decision. So one part we are making the edge to do the correlation, another part we are making the edge to do the decision. And finally, on the edge, what we can do is a distributed analytics. So edge, we can store data to certain extent on these devices. Maybe up to 24 hours of data about certain patterns can be stored. But processing requires a lot of CPU. So what we do is, we try to understand the ideal times your devices go. In a home, you are not continuously using your AP, right? Probably we tend to sleep when the devices become free. So those areas we run the analytics and then send them. We don't need to, suppose I want to baseline the connectivity, I don't need the data immediately. It's not a real-time data I want. I want to collect over a period of time. So I can do that analytics at the later part of time when this system is free. That way I offload a lot of processing to the edge. So this is a completely decentralized model which we have developed. So with this, we are still able to run our Evolve engine in a distributed fashion, a portion of it in the cloud and portion of it in the edge. So what we able to achieve with that is what the kind of data we used to collect in a centralized cloud is 1.6 gigabytes of statistical data per day has come down to just 10 MB. Right? And similarly, 500 MB of patterns which we collect has come to 0.34 MB per AP, and 1.2 gigabit of analytic data has come down to 35 MB of data. So with this, we are able to provide a feasible, cost-effective solution and still able to achieve what we want to achieve with our AI engine. So today, this engine being deployed, so these are the various actions we do. So there is certain things are done only by the cloud, certain things are done in a hybrid fashion. As I was telling, information is distributed, and some of these things are done at the edge, only at the edge. So what is done in the cloud is most of the prediction, multi-level learning, and obviously maturing. This is the feedback engine is obviously in the cloud. We cannot keep the feedback engine inside that. So whatever the data we have learned, this feedback, that evidential AI happens inside the cloud. And all the environmental, wherever you need environment, whatever the cloud has learned, it is again pushed to the edge to make the decisions. And certain things only happens in the edge, dynamic priority or coordinated action. So between, let's say you have a mesh network, you want to make sure that the client is moving from AP1 to AP2, and I want to decide whether the client should be in AP1 or AP2. Those decisions are left to the edge. The cloud never involves in those decisions. So this is how we achieve, we deployed our solution in the ISP network. So this is how our typical stack looks like. So we have our edge intelligence, which we call it as SOT, self-organizing device cluster. And then we have an analytics layer. And then we have the feedback system on the cloud. So a portion of this analytics happens within the edge itself, and portion of it happens in the cloud. And then finally, we have all those maturing algorithms, the cloud engine, which is very restricted to the cloud systems. So today, we have deployed this solution across 3 million CPEs, 20 million Wi-Fi access points across 10 geographies and 35 ISPs. And we are also deployed across various verticals. Recently, when we deployed in public Wi-Fi, it has resulted in a lot of cost savings for the service provider. So what we achieved with all these things, so we have given 10 million lives attached, and 2 million users are consuming internet for education today with uninterrupted service and reliable connectivity. And 500K users are now connected to healthcare and critical service. With this, our solution being deployed, ensuring that their connectivity is always up and running. That's the impact which we created with our solution. So on the ISP sides, they see their benefits as well on the cost. They have 87% issue resolution because we are able to provide precise insights to what's happening in the network. And then the support handling time has come down by 50%, and their visibility, that last mile visibility, has increased by 70%. And the advantage is that this is one of the data collected from the real deployment, from the public Wi-Fi deployments. So we see that as the number of devices increases, their cost saving is also going up. With the 5,000 AP rural Wi-Fi deployment, we have seen a cost saving of up to 80% in terms of advantage. So these are the various partners, OEM partners and service providers we work with today. I'm almost in the end of the presentation. I kept it very short as you asked me, Srikant. So you have any questions, please?
Yeah, so my question is, let's say today I have an AP or I am, let's say, designing an AP. Now, if I have to deploy your solution in my AP, so what is the memory, extra memory I need, or what are the extra CPU power I need that I need to be budgeted?
So we don't, so far we try to use whatever the window of CPU and memory you have. So to give a number, typically we use only 8 MB to 15 MB of your RAM and 10 to 15% of your CPU. And as I told you, certain cases where CPU crunching process happens, we will wait for your ideal times, right? Your system will go idle at certain point of time. Only those times we do the number crunching. So we try to accommodate our solution into the existing platform. We don't need anything extra.
Okay, yeah, thank you.
My question was very similar to that, but yeah, here.
Oh, sorry. Okay. Yeah.
So currently, who is using it? Any customers? Everybody.
So this is Excitel is one of the 4th largest ISP service provider who is located in the north part of the India. Most of the Indian ISP providers are using it. We are also in talks with the bigger names as well.
Okay. And one last question is, can you give us an example which particular problem was solved? Like it was sending so much of data, and after your solution, we are able to make a decision at the AP level.
There are a lot of things we have solved, but one interesting thing I could say was, so one of this device models, one of the ISP providers, they always had complaints that Zoom is not working onto their device. Okay. And they are not able to convince the OEM also what is the problem, and they are not also able to understand from the logs where the problem is, but they get a lot of complaints that Zoom is not working, Zoom is not working. So once they deployed our solution, so it was able to figure out that rate control algorithm, which is deployed on a specific model of AP, is having an issue whenever the client moves between an RSI range of 65 to 75. Whenever it goes there, the rate drops down and it is increasing the latency, and that is only reason why Zoom is very sensitive to latencies. All other streaming applications, YouTube or Netflix, they will not be able to see that problem. Only with Zoom it will happen, and since we have an application classification, it also classified the problem is only happening in Zoom, and that is because of the latency introduced by the algorithm of the AP.
Okay, basically you track all the apps.
We sense the application, we sense the radio metrics, we try to understand the inter-packet gaps, latencies, everything. That's what I was talking about, behavioral patterns, right? Okay. Every variation in the network is what we look at.
Yeah, so here, yeah. So I'm also looking for an example actually. If it's okay for you, can you take the mainstream names, like you can take a TP-Link and a good client, like take iPhone, if example, like can you tell with whatever analysis you did debugging?
Okay, one interesting thing I can tell about iPhone is that when you kick the iPhone client more than 3 times, let's say iPhone is not moving from one band to another, more than 3 times if you kick, iPhone has the ability to blacklist the AP, right? So this we can sense it. And then we know that, okay, this has already been, these 3 actions been done. Probably I will not do this at this point of time. So these kind of things, so many such examples I can give you. Yes?
So in the AP side, right, how much data you are capturing, like in data packets also capturing? By the
Everything we want to analyze,
okay.
But we don't capture anything. That's what we try to distribute that data analysis itself.
So analysis is done in the AP or cloud?
Analysis, I would say some of that happened in the AP, some of that happens in the cloud, so depending on the size of the problem. For example, if I want to understand whether a specific model or AP model has a problem, I will do it in the cloud because I collect data across all the models.
So if analysis is happening in the cloud, you have to send the data to the cloud, right?
Yes.
The bandwidth is accounted by the customer or ISP. Let's say for sending 1 GB data.
We use very less bandwidth, like 0.2 kbps or 0.3 kbps, that's all.
No, if data is used, then you have to send to cloud, right? Let's say 2 GB
Yes,
data.
that's what I'm saying. 0.3 kbps to 0.5 kbps is the amount of data or amount of data being pumped over a day.
Okay.
That is something ISP agreed. They are able to sell the solution. So,
Guhan, this is me.
Yeah,
So, do you collect the same set of telemetry across and then tweak it based on some request from ISPs, or how is it? You said you have a feedback cycle and you collect
No, we
data,
collect all the telemetrics required for every problem. So
always, superset it is it?
Yeah, what is it?
You always collect everything.
Always collect, but the processing, whether I do it on the edge or I do the cloud, is where I make the knobs.
Okay.
So that way I don't need to push all the data to the cloud.
So you just said, that, for example, some problem, if you have a statement of a problem, at that point, you don't have to go and collect more data. You just have to decide whether you want to use the data at the edge or at the cloud, is it?
Yes.
That's what
So
you're
basically, first I will try to understand whether this information, I call it as metadata, in our terminology we call it metadata, whether this information has to be sent to the cloud or not. That itself is, there is a decision engine which tries to understand that and then moves the data to the cloud if required. Only critical data is sent to the cloud. Most of the data is processed within the edge itself.
I have one more question. You said that behavior and the feedback, that is taken to the cloud and then published to all your other edges.
That is the okay, this is the part I think you are asking. So, yeah.
Somewhere there.
Yeah. So the learning is again distributed. Say, for example, I have detected that at RSSI minus 75, this particular client will, if I go and kick the client, it will disconnect. That information I will again push it back to the edge, so that next time edge doesn't need to send the same data again to me because it's already learned. So I tell you, for this particular you have already learned, this is your decision. So do that whenever it happens. Now decision also will be done by the edge. Data being sent also is avoided.
The question I had was, will you have scenarios where only certain deployments will be affected and you don't have to pass on this knowledge to everybody who is connected to you? Is there anything local about any of this?
Yes,
feedback?
yes, lot of things are very local because the way you have positioned the APs and the same iPhone will behave differently at different points of time. So that is why site level learning also we do. So that is a localized learning which we do. So that is again pushed on that site, only to that site.
Okay, thanks Guhan. Sorry, in the interest of time. Guhan is available, so post 5 o'clock we have a meetup, so please stay back and feel free to ask Guhan more questions. Thanks Guhan. Yeah.